Now let's look into how to apply Gauss's law to find the electric field in certain cases. So consider a filled sphere, or a ball, with radius r and a uniform charge density of ρ. What's the electric field E everywhere? Well, there's really two regions of interest here. Uh, of course, inside the ball and outside the ball. So let's start by talking about outside, although much of what we'll say will apply to both. So how do we use Gauss's law? Well, there's a couple steps we need to go through. The first step is we need to figure out in what direction should the electric field point. And generally, we're going to use symmetry to figure this out, the symmetry of the problem. So by the symmetry of our problem, we would expect that the electric field should only point in the radial direction. So it should be some magnitude times r hat. Actually, we can go a bit further. We can say that the electric field should only depend on r, the distance from the center, because, again, by symmetry, there's no reason it should depend on any of the angles. It should only depend on the distance from the center. Okay, so once we've done that, the next step in Gauss's law is to draw a surface that takes advantage of the symmetry of our problem. So we have a spherical symmetry in our problem here, and so it makes sense for us to draw a spherical surface. Let's draw a spherical surface. It's kind of an imaginary surface that we're drawing. We're going to call this some Gaussian surface, and it's going to have some radius little r. Notice that little r is different than big R, which big R is the radius of the filled sphere. Okay, so this Gaussian surface has a radius r, and since we're going to first look outside, this little radius r is going to be bigger than capital R. We look at a little area vector on the surface dA, and this little area vector dA is, well, it's whatever the area of that, and it's pointing in the r hat direction. Well, that means it's pointing in the same direction as the electric field, so E dot dA is really just E times dA. So once we've done that, now we can actually evaluate our flux integral. We can get pretty far on this because we have the integral over the closed surface of E dot dA. And note that this surface here, S, is our Gaussian surface, not the surface of our charge. And so this is some closed integral over E times dA, but E only depends on R, so it's constant over the whole surface. So we can pull that out of our integral, and then just we have a closed integral over the surface dA. But that must just be equal to E times the surface area of the sphere. So note that we took this complicated looking expression, and really all we need to know was the surface area of the sphere in order to do this integral. Okay, the next step in doing Gauss's law is to calculate the charge enclosed. So the charge enclosed is the volume integral of rho d tau. And if we look back at our setup here, our surface is enclosing our entire volume. So all of our charge is what's going to be enclosed. So we could just write that as whatever the total charge is. Let's do the integral here for future benefit. So it's going to be a triple integral because it's a volume integral. And it's the integral of r squared dr sine theta d theta d phi, where r goes from 0 to big R, theta goes from 0 to pi, and phi goes 0 to 2 pi. Okay, so we can do these integrals. Then we get rho times r cubed over 3 for the r integral. And then the angles give us a factor of 4 pi. So we get 4 pi over 3 r cubed times rho. And notice this is indeed just the volume times the charge per unit volume. But it's nice to see that come out of the integral explicitly. Once we have these two halves of Gauss's law, then we just put them together to solve for the electric field. So the closed surface integral of E dot dA is equal to 1 over epsilon naught, the integral of rho d tau. So that means we have E times 4 pi r squared is equal to 4 pi over 3 big R cubed times rho. Again, I want to point out that these are different r's. So there's a little r versus a big R. Little r is the size of our Gaussian surface. and that can change depending on the size of our surface. Big R is a constant. It's some fixed size of the charged sphere that we're given in the problem. Okay, so we can solve for the electric field as it depends on the distance r from the center. Forgot my factor of epsilon not there. Okay, so some factors of 4 pi cancel. So you get r cubed rho over 3 epsilon naught times 1 over r squared. This might make more sense if you write this as q total over 4 pi epsilon naught, 1 over r squared, where q total is equal to the total charge of the sphere, 4 pi over 3 r cubed times rho. And that actually makes a lot of sense. This looks like the electric field from a point charge. So for a charged ball like this, the electric field is just going to look like a point charge. That might have not been too obvious to you unless we used Gauss's law to actually calculate that. Let's look inside the sphere. So inside the sphere, let's redraw our charged sphere, charged ball. So as before, our first step is to draw a Gaussian surface inside of the sphere with some radius r, and now this little radius r is going to be smaller than the radius of our ball itself. Also, as before, the dA vector will point radially outward. So we have dA vector is equal to dA times r hat. And so that means we can write E dot dA, while E is still only depends radially, as just E times dA. This means that our flux integral, just as before, is actually just as simple. It's just the electric field times the integral of the area of our Gaussian surface. And so it's 4 pi r squared times E. So actually that part didn't change when we went inside. The other part of Gauss's law will. So now we need to calculate the charge inside of our surface that we've drawn here. And so the Q enclosed is a triple integral of rho d tau. And so that's an integral writing in for d tau. So we have rho r squared dr sine theta d theta and d phi. And the limits, well, we should write primes on those r's. The limits go from 0 to r for r prime, 0 to pi for theta, and 0 to 2 pi for phi. So these integrals can be done, and you get rho times r cubed over 3 times 4 pi. Or Q enclosed is just equal to 4 pi over 3, rho little r cubed. Notice again that this actually is little r cubed. It depends on little r. Also note that Q enclosed is actually 0 at r equal to 0. And that actually makes sense. You shouldn't have any charge at r equal to 0 if you have a sphere of 0 size. Also, if you let little r equal to big R, then you get Q enclosed is, well, what we had before for the total charge of the sphere, 4 pi rho over 3 times r cubed. So let's put this all together into Gauss's law. So the closed integral of E dot dA inside is equal to Q enclosed inside of the sphere over epsilon naught. Or that means the electric field times 4 pi r squared is equal to 4 pi over 3 rho little r cubed over epsilon naught. So 4 pi's cancel, and some of the r factors cancel in this case. So we find the electric field is rho over 3 epsilon naught times r inside of the sphere. And this is actually significant because it means the electric field actually increases as you leave the center. Also notice that the electric field is exactly 0 at the center, which is maybe what you would have expected. It should completely cancel at the center of the sphere. Let's summarize this information by making a quick plot of the electric field as it depends on r. So up to big R, the electric field is linear, and then outside of big R, the electric field falls off like 1 over r squared, like a point charge.